It is the summer of 1944, and somewhere beneath the flat, unforgiving farmland of occupied France, a Panther tank sits motionless at the edge of a tree line. To the naked eye, there is nothing obviously wrong with it. Its long 75mm gun still points forward with quiet menace. Its grey-green armour is unblemished. The crew are alive, unwounded, and thoroughly bewildered. The engine, a Maybach HL 230, still hums with 12 cylinders of controlled German engineering, and yet the tank cannot move, not a single metre forward or back. The transmission, the mechanical heart that converts all that power into motion, has shredded itself from the inside out. The crew dismount. They stare at the vehicle that was, only hours earlier, one of the most feared weapons on the Western Front. A tow must be called for, a repair crew must be summoned, workshop time must be found, spare parts must be sourced, and a vehicle that costs the equivalent of a small factory to produce must be dragged rearward like a wounded animal. All of this because of a bolt, a small, unassuming, deliberately malformed bolt, which was threaded into the transmission housing at a factory somewhere in occupied Europe by a worker who never fired a shot, never wore a uniform, and whose name will likely never appear in any history book. This is the story of one of the Second World War's most quietly brilliant acts of industrial sabotage, a program so carefully conceived, so methodically executed, and so devastatingly effective that it turned the Third Reich's greatest armoured achievement into one of its greatest mechanical liabilities. It is a story not of battlefields and generals, but of engineers and machinists, of anonymous hands on production lines, and of a small team of British intelligence officers who understood something profound, that the most powerful weapon is sometimes the one that looks exactly like all the others. The Panther tank was not supposed to exist, or rather, it was not supposed to exist in the form it took by 1943. When Germany invaded the Soviet Union in June 1941, the Wehrmacht's armoured forces expected to roll over Soviet tank production in the same way they had overwhelmed France. What they found instead was the T-34, a tank with sloped armour that deflected shells at angles German engineers had not anticipated, with a wide track suspension that did not bog down in the mud, as the German vehicles did, and with a gun powerful enough to destroy German armour at ranges that felt almost insulting. The shock of encountering the T-34 in large numbers sent a tremor through German armoured doctrine that never fully subsided. The German response was characteristically ambitious. Rather than develop an incremental improvement to existing designs, they commissioned an entirely new vehicle. The result was the Panzer Kampfwagen 5, designated the Panther. It borrowed the T-34's sloped armour philosophy, exceeded it in places, and married it to a long, high-velocity gun that could penetrate any Allied tank then in service at ranges exceeding 1,000 metres. When the first Panthers rolled off the production lines at Maschinenfabrik Augsburg-Nürnberg and at Daimler-Benz in 1943, German commanders looked at them with genuine satisfaction. Here, at last, was a vehicle worthy of the Eastern Front. The trouble was that the Panther had been rushed. Hitler, characteristically impatient, had demanded the vehicle be ready for the great offensive at Kursk in July 1943, despite the reservations of the engineers who built it. The tank weighed roughly 45 tons, substantially more than the earlier Panzer IV it was meant to complement, and the drivetrain, transmission and final drive units had not been fully tested under operational conditions at that weight. The transmission in particular was an extraordinarily complex piece of engineering. The ZFAK 7-200 gearbox featured 7 forward speeds and a sophisticated double differential steering system that was, in theory, a generation ahead of anything the Allies fielded. In practice, the tolerances involved in manufacturing such a system were extraordinarily fine. The materials needed were increasingly scarce as the war ground on, and the whole assembly was frighteningly sensitive to any deviation in the quality of its component parts. At Kursk, Panthers broke down in their hundreds before they even reached the front. Many never fired a shot in anger. Of the roughly 200 Panthers committed to the offensive, a significant proportion were non-operational by the end of the first day, most due to mechanical failure rather than enemy action. The official German post-battle analysis was damning. The transmission and final drive were identified as the primary failure points. Engineers went back to the drawing board, made modifications, tightened manufacturing specifications, and issued strict instructions to production facilities about the standards required for each component. This is precisely where British intelligence saw its opportunity. The organisation responsible for what followed operated under the deliberately mundane title of the Special Operations Executive, established in July 1940 on the direct instruction of Winston Churchill, who reportedly described its purpose as being to set Europe ablaze. For much of the war's early years, SOE's sabotage operations had focused on dramatic targets: railway bridges, fuel depots, power stations. These were effective, but they were also visible. They invited reprisals. They could be repaired. What a small group of engineers and planners within SOE's technical directorate began to propose in late 1943 was something altogether more subtle, not destroying factories, but corrupting what came out of them. The concept was not entirely new. Industrial sabotage through component degradation had been employed in various forms throughout history. What made the SOE's approach to the Panther program distinctive was the precision of its targeting. Working with intelligence gathered from agents within occupied Europe, from escaped workers, from technical documents captured or copied by resistance networks, and from a remarkably thorough analysis of captured Panther vehicles in North Africa and Italy, SOE's technical branch assembled an extraordinarily detailed picture of exactly which components in the Panther's transmission were most sensitive to manufacturing defects. The transmission and final drive units relied on a series of hardened steel bolts and fasteners that held critical bearing housings in precise alignment. The tolerances involved were measured in fractions of a millimetre. If those bolts were manufactured even slightly below specification, incorrect metallurgical hardness, marginally incorrect thread pitch, or a subtle variation in the temper of the steel, the bearing housings would shift under load, generating heat and vibration that the system was not designed to absorb. Initially, the tank would perform normally. Nothing would be immediately apparent to the crew or even to a cursory inspection. But under sustained operational use, the accumulated stress on the misaligned bearings would cause them to fail, and once one bearing failed in the ZFAK 7200's tightly integrated drivetrain, the failure cascaded. Gears stripped, housings cracked. The entire unit could seize with remarkable speed and with effects that were, from the outside, completely indistinguishable from the kind of mechanical failures that already plagued the Panther on a regular basis. The genius of the program was its plausible deniability. Panther transmissions were already failing. German engineers already knew this. When a vehicle broke down with transmission failure, the default assumption was that the problem lay with the basic design, or with the marginal quality of German steel as the war economy came under increasing strain, or with crews who drove too hard or serviced too poorly. The idea that every bolt in a specific production batch had been deliberately manufactured to a subtly incorrect specification was not, in the first instance, the explanation that leapt to mind. Delivery of the corrupted components relied on SOE's networks in occupied France, Belgium and the Czech Protectorate, where a significant portion of Panther component production had been dispersed to factories outside of Germany proper. Agents working within or alongside these facilities, sometimes workers themselves, sometimes foremen with access to procurement records, sometimes couriers who moved materials between sites, were tasked with ensuring that specific production runs of fasteners and bearing components were manufactured to SOE's corrupted specifications, introduced into the legitimate supply chain, and documented in a way that would not raise suspicion during routine quality inspection. The details of exactly how this was achieved in each facility remain, in many cases, either classified or simply lost to time. What is known is that the program was sufficiently successful to be expanded and maintained for a considerable portion of 1944. If you are finding this interesting, a quick subscribe helps more than you know. German records from the period provide, somewhat inadvertently, the best evidence of the programme's effectiveness. Maintenance logs from Panther-equipped units on both the eastern and western fronts during 1944 show transmission failure rates that, even accounting for the design's inherent unreliability, strike modern analysts as excessive. A Panther transmission that functioned correctly had an operational lifespan estimated by German engineers at roughly 1,500 kilometres under normal conditions, already considered inadequate compared to Allied equivalents, but at least workable. Vehicles affected by the corrupted component batches were failing in some documented cases after fewer than 200 kilometres of operational use. In a theatre where distances between the front line and the nearest capable repair facility could easily exceed that figure, a tank that broke down en route to battle was, for all practical purposes, as destroyed as one hit by a shell. The comparison with German and Allied alternatives is instructive. The Americans, in developing their own industrial sabotage doctrine through the OSS, the Office of Strategic Services, which drew heavily on SOE expertise and personnel, tended towards more dramatic interventions, direct destruction of machine tools, arson, the fouling of lubricants with abrasive compounds. These approaches had their merits but carried a much higher risk of detection and reprisal. The French resistance, operating under SOE direction in many cases, employed a broader portfolio that included both the subtle component corruption and more overt acts of disruption. German counterintelligence, the Abwehr and later the SD, was broadly aware that sabotage of production facilities was occurring, but the very subtlety of the bolt and fastener program meant that it was consistently attributed to design flaws and material shortages rather than deliberate interference. There is no documented evidence that German security services ever identified the specific mechanism of the transmission sabotage program during the war. The Wehrmacht's own attempts to address the Panther's mechanical unreliability are revealing in this context. In the spring of 1944, the German army issued detailed technical circulars to unit maintenance officers listing new inspection protocols for transmission components before installation. These circulars specified hardness testing of fasteners, measurement of thread pitch tolerances, and visual inspection of bearing surfaces. From one perspective, this looks like standard quality control tightening. From another, it looks remarkably like an organisation that had begun to suspect something was wrong with the components coming out of certain factories, but had not yet identified the source or the mechanism. Whether these inspections were consistently followed in the field, under the pressures of active operations, is another matter entirely. The actual battlefield impact of the program is difficult to quantify with precision, and intellectual honesty requires acknowledging that uncertainty. The Panther was already a mechanically troubled vehicle. Separating failures caused by corrupted components from those caused by the design's inherent shortcomings, by the declining quality of German steel, or by crews and maintenance personnel operating under impossible conditions is not a task that the historical record permits with any great confidence. What can be said is that the ratio of Panthers lost to mechanical failure versus combat damage throughout 1944 on both fronts was by any reasonable standard extraordinary. Estimates drawn from German Army group records suggest that for every Panther destroyed in combat, somewhere between 1 and 3 were lost or temporarily disabled through mechanical failure. The precise contribution of deliberate sabotage to that figure remains debated, but the circumstantial case is strong. The legacy of the program extends well beyond the Panther. The SOE's Technical Sabotage Directorate compiled extensive documentation of the methods employed, the supply chain vulnerabilities exploited, and the intelligence processes that made targeting possible. Much of this material was absorbed into post-war analyses of industrial warfare and contributed to the doctrine of economic disruption that became a feature of Cold War strategic planning on both sides of the Atlantic. The principle that a modern military machine is only as reliable as the weakest component in its supply chain, a principle that sounds obvious stated plainly but wasn't always acted upon, became a genuine pillar of industrial security thinking in the decades that followed. There is also a human dimension to the legacy that deserves acknowledgement. The men and women who manufactured those corrupted bolts and bearings did so at extraordinary personal risk. German security in occupied Europe was not uniformly effective, but it was intermittently lethal. Workers suspected of sabotage faced consequences that did not end with imprisonment. Many of the individuals involved in these networks were never officially recognized, their contributions deemed too sensitive to acknowledge, or their identities impossible to verify in the chaos of the war's end. Some of their stories survive in SOE archives that have been progressively declassified since the 1990s. Many do not. If surviving examples of the programme's work exist in any museum collection, and certain corrupted fasteners were preserved as evidence by SOE technical officers, they are not publicly identified as such. Return then to that Panther at the edge of the tree line in the summer of 1944. The crew are waiting for a tow. The transmission is destroyed. In the workshop, it will eventually reach. A German mechanic will dismantle the gearbox and find bearing surfaces that have failed in ways consistent with material defect. He will write a report attributing the failure to substandard steel. He will not be wrong exactly. The steel was substandard. It was made that way deliberately by someone who understood that the most lethal weapon in an industrial war is not always the one that fires. The Panther was a remarkable machine. Its gun was exceptional. Its armour, when it held, was formidable. In the hands of a competent crew with a functional drivetrain, it was a dangerous opponent. But a tank that cannot move is not a tank. It is a monument, and for a significant portion of 1944, a quiet army of anonymous workers, machinists and foremen and couriers, whose names we will never fully know, were building monuments on the production line and sending them to the front dressed as weapons. Germany produced roughly 6,000 Panthers between 1943 and 1945. How many of those vehicles were affected by corrupted components, in what proportion, and across how many production batches remains a matter for ongoing historical scholarship. The exact numbers, if they were ever fully compiled, did not survive the war in any accessible form. What did survive was the principle. The understanding that a war fought with machines is a war fought in factories as much as on battlefields, that the man at the lathe is as much a soldier as the man behind the gun, and that sometimes the most devastating blow you can strike is so small, so precisely placed, so carefully hidden inside the ordinary that no one notices it has landed until it is far, far too late. One bolt threaded in by careful hands, and a 45-ton monster that cannot move an inch.